Welcome back. Last time we talked about a perfect metal. So within the perfect metal, we cannot have E field, and also we cannot have charge distribution. But when we have a metal dielectric interface, we can have some charges being deposited on the interface. But due to the fact we have metal underneath, we can only have normal E field lines. We cannot have tangent E field lines. Why not? Because if we have the tangential E field line inside the metal, we cannot have E field. So curl of E equals to 0 must apply across this boundary. So we cannot have the tangential E field line. We can only allow to have normal E field lines. Today we're going to continue to explore about metals. In this case, we have a metallic shell. So the shell is spherical. It has an inner radius, Ri. I represents inner. And the outer radius, Ro. Alright? So this is what we define as the metallic shell. And somehow, fictitiously or magically, we can put a charged cube inside the shell. And we want to investigate how the shell is responding to the presence of the charge. Right? So we are going to look into the charge distribution on the metallic shell, and we are going to derive for the resulting E field intensity as well as the electric potential. But first thing first, again, for this given geometry, which orthogonal coordinate system should be used? The shell is spherical, and the point charge emits field lines in a radiant way. So the preferable coordinate system is again spherical coordinate system. Right? So we are going to use spherical coordinate, and we are going to use Gauss's law because we have a very symmetric geometry. So let me walk you to the board, but before we do that, we are going to discuss and analyze this problem into 3 different spatial regions. The first one is my observer is outside of the shell. I'm going to invoke Gauss's law. Second region is if the observer is within the shell, magically, don't ask me why, but if you have an observation point inside the shell, then the result should be very different as compared to outside of the shell. Third region is when your observation point is inside the shell. Right? So we are going to classify the analysis into 3 different spatial regions: outside, inside the shell, and within the shell. Right? So let's walk to the blackboard and ask ourselves, well, because you have forced a charge into the metallic shell, I'm only drawing the cross-section again. So we know that for a given point charge, we assume it's a positive charge. So it emits radiant E field lines. That has been known for the past 9 class hours. Right? So ask yourselves, when you have field lines, they start from positive charge and somehow they end on the inner radius of your metallic shell, what is that going to do to the metal? Well, you know that along the metal dielectric interface, you are allowed to have charge deposition, right? And that resulting induced charge can have normal E-field lines. So it is proper for us to draw some induced charge depositions, okay? Now the sign of the induced charge must be negative. Why? Because E-field lines starts from a positive charge and terminates at a negative charge. So this is telling you, initially, if you only have this metallic shell, its charge is neutral. Being metal, it has a lot of free electrons, but it's uniformly distributed. Now, with the presence of your charge, the inner shell will have a lot of induced, or you're trying to redistribute the electron profiles. So the electrons will be attracted by this positive charge, so the entire inner shell will be covered with lots and lots of electrons, right? And the sum of all these negative charges would be Q, but having a negative sign, right? On the other hand, as I mentioned, the metallic shell started as a charge-neutral material. So the charge needs to remain neutral. What does that mean? That means currently your inner shell is having a lot of electrons. So seemingly this metallic shell is now negatively charged. But that cannot be true because initially it was started as a charge-neutral device. So at the same time, you need to have positive charges deposited or dispersed on the outer shell. Okay? So you have one induced electron, you have one positive charge, right? So overall, your metallic shell remains to be charge neutral. So I'm going to use the yellow color to denote all these positive charge densities adds up to Q. All right? So without the central charge, this metal is just everywhere charge neutral. But having this charge, the inner radius, the inner sphere, is filled with negative charges. The outer shells are filled with positive charges. But overall, the metal itself remains charge neutral if you add the charges all up. Right? So now let's try to analyze this system and its resulting E-field intensity. Because this geometry is perfectly symmetric, so using Gauss's law is the smartest choice. So how to invoke Gauss's law? If I have an observation point or an observer here at P, how should I invoke Gauss's law? Gauss's law tells you if you form a closed surface, You form a closed surface, and you're trying to ask yourself how much charge is being encompassed by this surface. And then those charges give you the E field intensity. So if I'm standing here and I form a closed surface, like a sphere, right? I have a spherical surface touching this P point is closed, and I ask myself, hey, there's no charge inside, so at this point there is no E field. Is that correct? That cannot be correct. Right? Because the problem we're trying to analyze is due to this charge and due to this spherical shell of metal, what is those combination going to affect my observation point? All right? So somehow this closed surface needs to include the sphere, the shell, and the charge. So I should be using a very big sphere, right? I should be using a very big sphere. So the radius is r, right? Starting from the charge all the way to my observation point. That's my radius. And I have a very big closed surface to include the charge as well as the shell. Now, for this case, right? So I know that somehow, due to spherical coordinate symmetry, all the field lines are radial, and I know the surface area is 4 pi r squared. And then the question is, for this enclosed surface, how much charge is being encompassed? Well, let's count. I have my initial charge, right, Q, and I have all this induced negative charge, which adds up to negative Q. And then I also encompass all these induced positive charges, which adds up to Q again. So basically you have Q minus Q plus Q. Take a good look. So this is telling you, when we are standing outside of this shell, when we're outside of the shell, the electric field intensity being felt at the observation point is exactly identical to just having the charge. So the shell is really doing nothing, right? You still remember this result, right? Q over 4 pi epsilon 0 r squared is the E field intensity for a single charge. So this is actually telling you, having this shell or not, there's no difference. Okay? Alright, so that's case number one. We're standing outside of the shell. What happens if we stand inside? If our observation point is inside the shell, meaning the radius r is greater than ri and smaller than ro. So now I can form a second closed surface, right? So then the question is, how much charge is being encompassed by this closed surface? You have the initial charge at the center, and you included all these induced negative charges, which adds up to negative Q. So Q minus Q is 0. And this tells you, well, Gauss's law tells you, as long as you are within the metal, you don't have net charges. Well, the net charge sums up to 0. And therefore, you don't have electric field. This is not very contradictory because, as we mentioned, for ideal metal, inside the metal, you cannot have E field, and inside the metal, you cannot have charge distribution, right? So this is not very surprising. Inside the metallic shell, you have no field. So this is a very nice demonstration of using Gauss's law. It's so simple, right? You don't really need to perform integration. You only need to take account of the net charge enclosed by your surface. Alright, so that again tells you if you don't have fields, the entire shell is having a constant potential, right? Constant potential. Now let's walk inside towards the center. So now we're really within the shell. Within the shell, you can form another closed surface, which is also a sphere, but having a radius smaller than Ri. For this case, for this closed surface, you only encompass the initial charge, Q. So again, your E field is non-zero. Again, it's like Q divided by 4 pi epsilon 0 R squared. It conforms to the E field intensity of a single charge again. So the effect of this metallic shell is very apparent. Within the shell, there's no effect. Outside of the shell, there's no effect. You cannot really tell the difference you have this shell or not, within or outside of it. It's only really inside of the shell you feel its presence because you don't have E field intensity. Right? So outside of the shell, within the shell, you have well-defined E field intensity, which obeys to Coulomb's law. Right? It's somewhere within the metal. Suddenly, you have abrupt field jumps all the way to 0. Okay? So this is the entire profile of the system. The charge plus the metallic shell. So once we have the E field distribution, we can just perform integration, line integration, to retrieve the electric potential. We only have to perform integration, right? So we start from outside. Infinitely far means potential equals to 0. We integrate all the way up to here, Rho. So when we're outside of the shell, the potential is Q divided by 4 pi epsilon 0 R. Again, identical to a single charge. So with or without the shell, doesn't make any difference outside. Right? For this region, within the metal, because you don't have E fields, so there's no need for you to perform the integration. Integration of 0 means 0. So this entire region within the shell, within Ri and Ro, you have a constant potential. And that constant potential is Q divided by 4 pi epsilon 0 Ro. Right? So for the entire metal, you have a constant potential. Okay? For the region inside the shell, we can perform integration. But again, when we perform integration, the most important issue is, in integration, you always need to add a constant. And that constant for the inner region is the potential of this region. You need to add it up, right, during integration. So the result is slightly complicated, right? For a test, whether you obtain a correct result or not, for a test, you should be able to insert the R value to a particular value to see whether it makes sense. So in this case, when we're trying to derive the electric potential as a function of space, we are most interested in R equals Ri. It needs to reduce to this result. Okay? So R equals Ri, these two are cancelled, so the potential is Q divided by 4 pi epsilon 0 divided by Ro, which makes sense. Right? Which converges to this constant potential. And this potential is equal to the potential of the outer region at Ro. So everything makes sense. But let's try to talk in more details. This is a very simple case, but it contains a lot of information. First question to you. Well, as we mentioned, by default, we almost defined within a perfect metal, we cannot have electric field. And in this case, indeed, there is no field within the metal. But why is there no field inside the metal? Take a good look at the picture I drew. Take a good look at the induced charges on both metal-air interfaces. At the inner surface of the shell, I have induced negative charges, right? And due to charge neutrality, the outer part has positive charges. So to answer why within the metal you have no net field, it's very simple. Let me use another color to see whether red appears good. Okay? If you have this positive charge and you have the negative charge, how can you just draw the resulting field lines? Well, field lines start from a positive charge and terminates on a negative charge. Right? So the meaning of this metallic shell is the induced charges are there so that these charges help to protect the metal being field free, right? This field strength is used to counteract the field strength of this center charge. So you have this is due to Q, E due to Q, and you have E due to the induced charges. So the purpose of having the induced charges is to cancel out your external field strength. Right? So inside the shell, you have cancellation, but outside, you don't have cancellation. Okay? So again, outside of the shell, you have field. Within the shell, you have the field. But exactly inside the metal, you have no field. Okay? So these charges are used to cancel out your external field lines.